Alright, let's get into a topic that really changes how we solve real world problems. We have talked about linear programming before, but today we are moving into integer and mixed integer programming. Okay, so why do we care about this? Well, in standard linear programming, we assume variables can be any fraction. But think about it. You can't exactly produce half a car or hire two-thirds of an employee. And that's where MIP comes in. It extends what we already know by letting some or all of our decision variables be integers. And this is huge for modeling discrete decisions like those yes or no choices we face in business, or dealing with indivisible quantities. To solve this, we use tools like the Gurobi and MIP solver. So it's incredibly fast because it uses some pretty heavy duty techniques. We are talking about things like branch and bound tree searches, cutting planes, specifically Gomori cuts, and advanced heuristics to find the best possible answer quickly. Okay, let's continue. Before we look at the code, let's make sure we are clear on the types of variables you will be working with. First, you have your standard continuous variables. Okay, let me show you. Okay, these can be any real value within their bounds. Then we have integer variables, which are strictly whole numbers. If you have a decision that is strictly either or, we use binary variables, basically just 0 or 1. Actually, there is also something called semi-continuous variables, and these are interesting because they are either exactly 0 or they fall within a specific range. It's like saying a machine is either turned off or off its own. It has to run at least at a certain minimum capacity. Okay, now let's see how this looks in Python using the Gurobi. Now, after we import our modules here, Gurobi Py, GP and GRB, after we import our modules and initialize our model, we start adding variables. Okay, let's see. Look at here what's happening. We define x count. Here we set the lower bounds LB to 0 and the upper bounds UB to 100. By setting the v type here to grb continuous, we are telling the solver this can be any number like 10.5 or 99.9. Okay, but what if we need whole numbers? We define x int, look at here, and the bounds are 0 to 50, but notice the v type is now grb integer, and this forces the solver to only consider 1 to 0 and so on all the way up to 50. Okay, now that's cool. Moving on to those yes no decisions. Here we create x bin. By using grb binary here, we don't even need to set bounds. The solver knows it's either 0 or 1. Now remember those semi-continuous variables I mentioned here, x semi. Here the lower bound is 10 and the upper bound is 100. Because it's grb semi count, the solver allows the variable to be exactly 0 or any value between 10 and 100. It can't be 5, for example. That's okay. And we can even take that a step further with semi-integer variables. As you see here, this x semi-int here is either 0 or a whole number between 5 and 20. But wait, what if you have a lot of variables to create? You don't want to write a line for every single one. And here we define a list of items A, B, and C. Then using model add vars, we create a whole set of binary variables for those items in one go. Okay, actually, in real engineering or business cases, you will often deal with multi-dimensional data. And look at the bottom here, we have three factories and four time periods. Instead of creating 12 separate variables manually, we use model add vars here and pass in both the factories and periods lists. We set the type to integer and name it prod. And this creates a two-dimension array of variables that we can easily reference later in our constraints. It makes the code much cleaner and easier to manage as your models grow. So, do you see how these different types allow us to be much more specific about how the real world actually works? Okay, and that part is done. Now, classic MIP example. Let's see here. Knapsack. We are going to walk through two classic problems that show exactly why mixed integer programming is so powerful in engineering and logistics. First up is the 01 knapsack problem. Here, 01, and now think of this like a packing challenge. You have a limited capacity and you have to decide which items to take to get the most value without breaking your back. It sounds simple, but this is a fundamental building block for resource allocation. We can't take half a camera or a third of a laptop, right? So this is a perfect case for binary variables. Now, look at how we set these up. In Gurobi, we define our items in a dictionary where each one has a value and a weight. For example, the laptop has a value of 10 and a weight of 5. Our total capacity is 10, and we initialize our model with GP model, as you can see here, and name it knapsack here. Okay, and here's the logic. Look at that. We create our decision variables. Okay, and notice we use v type grb binary, and this means x will be 1 if we pick the item and 0 if we don't. Then for our objective, we want to maximize the total value. Look at that. Here we use GP quick sum to multiply each item's value by its binary variable and sum them all up. The math here is basically the sum of value sub I times x sub I. Okay. And but we can't just take everything, right? We add a constraint, and again we use quick sum. Let me show you here quick sum. To calculate the total weight, that's weight sub I times x sub I, and we tell Gurobi it must be less than or equal to our capacity. Once that's set, we just call model optimize, as you can see here. And the solver finds the best combination for us. Okay, and facility location problem here. Something more complex, capacitated facility location problem. Let's say you are a logistics manager. You have three potential locations for warehouses and 5 customers. Each warehouse has a fixed cost to open it and a maximum capacity. There is also a cost to ship items from a specific warehouses to a specific customer. The goal is to decide which warehouses to open and how much to ship from each to minimize total costs. Okay, And looking at the setup, we have our facilities F1, F2, F3 and customers here. We define the fixed costs, the capacities, and the individual customer demands. And we see the uh, trans costs here, as you can see. And uh, that dictionary, which maps out the shipping price between every possible facility customer pair. Okay, and well, this is where it gets interesting because we are mixing variables. Now, look at that y variables. Y is a binary variable. If it is 1 if a facility is open, 0 if not. But x is a continuous variable representing the actual amount shipped. Since shipping amounts can be fractional in this model, ensures, LB is 0 ensures we don't have negative shipments. Okay, here, that's important. And here look at the objective function. We are minimizing two things. What are they? The sum of fixed costs for the opened warehouses and the sum of all shipping costs. After that, we need to make sure every customer gets what they need. Okay, and we loop through each customer and add a constraint saying the sum of shipments to them must exactly equal their demand. Okay, and actually, here's the most critical part, the capacity constraint. Here, we say the total shipments out of a facility must be less than or equal to its capacity times y. And think about the logic here. If y is 0, meaning the warehouse is closed, the right side becomes 0, forcing all shipments from that location to be 0 as well. If y is 1, the facility can ship up to its full capacity. And this is how we link a binary decision to a continuous flow. Okay, and finally we run optimization, and if Gurobi finds an optimal solution, we print the total cost and list which facilities were actually opened. It's a complete system deciding where to invest and then how to operate that investment efficiently. So, by combining these yes no binary variables with continuous flow variables, you can model almost any complex business operation. Pretty cool, right? Okay, now everyone, now that we have seen how to build these models, we need to talk about how to actually control the solver and how to know when a solution is good enough. And this is where the real engineering intuition comes into play. First off, you need to understand concept called the MIP gap. When Gurobi is solving these integer problems, it's keeping track of two values, the best solution it has found so far and the theoretical best bound it thinks is possible. The gap is basically the percentage difference between these two. It's calculated as the absolute value of the best bound minus the best solution divided by the absolute value of the best solution minus, uh, you know, and if that gap is 0%, you have mathematically proven you have the absolute best answer. But here's the thing, in the real world, getting to 0 can take forever. Usually a gap between 1 and 5% is perfectly fine for most business applications. Okay, here, and so how do we tell the solver when to stop? Well, we use parameters here. By setting model params MIP gap here to 0.01, we are telling Gurobi to stop once it's within the 1% of the best possible answer. And we can set a time limit, as you can see here, of 2600 seconds. This is a safety net. It says, hey, even if you have not hit the gap target, stop after 1 hour. And this is super important for automated systems where you can't have a script running indefinitely. And tuning, now sometimes you want the solver to behave differently based on your specific call. And look at that MIP focus. Actually, there are four main ways to use this. If you set to one, we'll focus almost entirely on finding any feasible solution quickly. This is great if you just need a plan right now. And if you set to two, it focuses on proving optimality, which means it works harder on moving that best bound we talked about. If you are feeling aggressive, you can also adjust how much time is spent on heuristics or cutting planes to try and shake out a better solution faster. Okay, and once the solver finishes, you don't just take the number and run. You need to check quality. We print the best solution found and the final gap. Seeing that nodes explored um, is also helpful because it tells you how much work the branch and boundary actually had to do. If the gap is still huge, you might need to rethink your model. Okay, final part. And speaking of rethinking the model, let's wrap up with some common traps. One big one is using a big M value that is too large. If you are using a huge number like in billion just to turn a constraint on or off, it actually makes the math much harder for the solver and slows everything down. You should always try to use the smallest m that still makes sense. Also, watch out for symmetry. If you have five identical machines, the solver might waste time checking every single combination of them even though they are the same. You can add symmetry breaking constraints to tell the solver, look, machine 1 is always used to before machine 2. Finally, always provide tight bounds, and if you have a decent starting guess, use a warm start to give the solver a head start. Alright, that's the big picture. You have got the variables, the models, and now the controls to actually make this work in production.